There's no science data yet, but they're confident that all of the instruments are still working. It's just a case now that we need different software to go onto different parts of the chip in order to access that science data again. For years, spacecraft have led the charge in exploring the unknown, but now Voyager 1 has sent back some data that has scientists feeling uneasy. This isn't just a glitch, it's a mystery that's raising serious questions. What could be out there, billions of kilometers away, affecting Voyager 1's systems? Let's go back to the beginning. On September 5, 1977, Voyager 1 launched from Cape Canaveral, Florida, on a Titan III-E Centaur rocket. Just 13 days earlier, on August 20, 1977, its twin, Voyager 2, had started its own mission. Their original goal was simple: study the moons of Jupiter and Saturn. But these probes did much more than that. They ventured far beyond, into the edges of our solar system, and kept sending back data that amazed scientists. Voyager 1 and 2 became the first human-made objects to explore space beyond the sun's influence. They've given us a treasure trove of information, from discovering moons around Jupiter and Saturn that are geologically active, to flying past Uranus and Neptune and revealing secrets we never expected. But now, Voyager 1 is sending back data that's strange and unsettling. Could it be something out there in space that's causing this? Or is the spacecraft itself changing after so many years in the harsh environment of space? With the Voyager missions expected to end around 2030, this unexpected development is troubling. It's not just about solving a technical issue, it's about understanding what's happening out there. As we keep gathering data, we have to ask ourselves, have we stumbled upon something far bigger than we ever imagined? Neptune's largest moon, Triton, is one of the coldest places in the solar system, where winds can range up to 1,000 miles per hour and surface temperatures plummet to a bone-chilling -391 degrees Fahrenheit. But that's not all. Voyager 2's discoveries on Triton revealed something even more mind-boggling: ice volcanoes that spew frozen particles and nitrogen gas, painting a picture of a world we never imagined. As Voyager 2 ventured further into the outer planets, Voyager 1 took a risky path, skimming dangerously close to Saturn's moon, Titan. This encounter revealed Titan's thick, hazy orange atmosphere and its complex chemistry, challenging everything we thought we knew about these distant worlds and leaving scientists with more questions than answers. The Voyagers weren't just any spacecraft, they were marvels of engineering, designed to be stable platforms that rotated over 15 times slower than a clock's hour hand, ensuring clear images even as they hurtled through space. Months before they reached Jupiter, these probes were already sending back breathtaking photos of the gas giant's swirling clouds and its iconic Great Red Spot, captivating everyone at NASA's Jet Propulsion Laboratory. But the real game-changer came when Voyager 1 discovered active volcanoes on Jupiter's moon Io. Slightly larger than Earth's moon, Io turned out to be the most volcanically active body in the solar system, shattering previous beliefs and dramatically changing our understanding of these far-off worlds. Among the many groundbreaking discoveries, one stood out. Europa, another of Jupiter's moons, might harbor a vast ocean beneath its icy surface, sparking the tantalizing possibility of extraterrestrial life. Similarly, geysers on Saturn's moon, Enceladus, hinted at liquid water beneath its frozen crust, fueling further missions to uncover more about these mysterious moons. Voyager 2's close encounters with Neptune and Uranus were equally stunning. As it approached Uranus, the probe revealed a blue-green planet with a complex magnetic field and an array of moons, including the intriguingly active Miranda. Then, in 1989, Voyager 2 gave humanity its first detailed look at Neptune, unveiling its deep blue atmosphere, the enigmatic Great Dark Spot, and confirming the presence of faint rings and 6 previously unknown moons. As the Voyagers journeyed deeper into space, their instruments continued to send back vital data. They provided key insights into the heliosphere, a bubble-shaped region of space influenced by the sun's magnetic field and solar wind. After crossing the heliopause, the boundary marking the edge of the heliosphere, the probes began exploring the interstellar medium, the sparse, mysterious space between stars. One of the most startling recent discoveries from the Voyagers was an unexpected increase in cosmic rays in interstellar space. This finding has forced scientists to rethink their theories about the environment beyond our solar system, shedding new light on the interstellar medium and the forces shaping our galaxy. The Voyager's incredible longevity and the wealth of knowledge they have provided are a tribute to the ingenuity and dedication of the scientists, engineers, and technicians who built and operated them. Their work has forever changed our understanding of the cosmos, and the Voyager's legacy will continue to inspire future generations of explorers. Despite the extreme conditions and vast distances, the Voyager spacecraft have persevered, providing data that has transformed our understanding of the solar system and beyond. These missions have underscored the critical role of robotic exploration in advancing our knowledge of the cosmos. NASA has taken steps to conserve the remaining energy of the Voyagers, carefully managing their power supplies and shutting down non-essential systems to prolong their missions. As these spacecraft approach the end of their operational lives, they are expected to continue sending back data until at least 2030. This information will further deepen our understanding of the interstellar medium and the outermost regions of the solar system. But the legacy of the Voyager missions extends beyond scientific discovery. Each spacecraft carries a golden record, a time capsule of Earth's diverse life and culture, intended as a message to any extraterrestrial civilization that might one day encounter them. This gesture reflects humanity's enduring desire to connect with the cosmos. The Voyagers have captured some of the most breathtaking images in space exploration. Among these were the unusual signals detected from Io, Jupiter's moon, revealing a volatile landscape with towering volcanic plumes. The iconic Pele volcano on Io stands out, with eruptions that reach heights 30 times greater than Mount Everest and span an area the size of France. The Voyagers took over 33,000 images of Jupiter and its moons, showcasing the planet's grandeur and the incredible diversity of its satellites. Since their launch, the twin Voyagers have continued to defy expectations. One of the most surprising discoveries was the faint rings of Jupiter, adding to the mysteries surrounding the gas giant. Voyager 2 also challenged earlier theories when it found that Europa, one of Jupiter's moons, has an icy crust over 60 miles thick. This discovery opened new avenues for planetary science, encouraging researchers to explore the potential habitability of icy moons. After their mission at Jupiter, the Voyagers received a crucial gravity boost that propelled them towards Saturn, allowing them to escape the Sun's gravitational pull and venture further into space. At this point, the two spacecraft separated, each embarking on its own path into uncharted territory. Voyager 1's close encounter with Titan, Saturn's moon, revealed a thick orange atmosphere, sparking further research into Titan's complex chemistry. Voyager 1 then headed north, leaving the planetary system and beginning its journey beyond our solar system. Meanwhile, Voyager 2 embarked on an extraordinary journey to the outermost planets. In 1986, it made a flyby of Uranus, discovering 10 previously unknown moons and expanding our understanding of the planet's satellite system. 3 years later, Voyager 2 reached Neptune, uncovering remarkable features of this distant ice giant. The spacecraft recorded wind speeds of up to 1,000 miles per hour, the fastest ever measured on any planet in the solar system. As Voyager 2 approached Neptune's methane-rich azure atmosphere from a distance of nearly 3,000 miles, it provided unparalleled views of the planet. It also discovered that Triton, Neptune's largest moon, is one of the coldest places in the solar system, with surface temperatures plunging to minus 391 degrees Fahrenheit. Triton's icy surface is marked by unusual geological features, including ice volcanoes that erupt up to 3 miles high, releasing frozen particles and nitrogen gas into its thin atmosphere. These findings have dramatically expanded our knowledge of the variety and complexity of celestial bodies in the outer reaches of our solar system. The Voyager missions have done more than just collect data. They've rewritten the history of space exploration, revealing the astonishing diversity of our neighborhood and inspiring future generations to continue the quest to understand the universe. The Voyager spacecraft have delivered invaluable data during their interstellar travels, especially in studying the heliosphere, a vast, bubble-shaped region dominated by solar wind. This study reached its peak when the spacecraft crossed the heliopause, the boundary where interstellar space begins and the solar wind's influence fades. Voyager 1 and Voyager 2 became the first human-made objects to enter interstellar space, achieving this milestone in 2012 and 2018 respectively. This transition advanced our understanding of the boundary between our solar system and the rest of the galaxy, offering scientists a wealth of information on the characteristics of magnetic fields and interstellar plasma. Astronomer Carl Sagan played a key role in these missions, advocating for a final set of photographs before the onboard cameras shut down. On Valentine's Day in 1990, Voyager 1 captured 60 images, including the iconic pale blue dot, a photograph of Earth from 3.7 billion miles away. This image, showing Earth as a tiny pale blue speck, remains a powerful reminder of our place in the universe. For over 40 years, the Voyager missions have delivered crucial data using technology from the 1970s, including 8-track cassette tapes for data storage. These tapes have endured high temperatures, the vacuum of space, and cosmic radiation, preserving invaluable scientific information about the outer planets, their moons, and interstellar space. The durability of these cassettes demonstrates the ingenuity of the spacecraft's creators. Voyager 2's encounters with Neptune and Uranus revolutionized our understanding of these distant planets. The probe discovered that Uranus, a seemingly featureless blue-green planet, harbors many moons, including the geologically active Miranda, and possesses a complex magnetic field. In 1989, Voyager 2 provided humanity with its first detailed photographs of Neptune, revealing the planet's vibrant atmosphere, deep blue color, and the Great Dark Spot. The spacecraft also confirmed the presence of weak rings around Neptune and discovered 6 additional moons. As the Voyager spacecraft continue their journey into interstellar space, they keep delivering crucial data on the heliosphere, the region dominated by the Sun's magnetic field and solar wind. After crossing the heliopause, the probes began investigating the interstellar medium, the sparse environment between stars. One of the most astonishing recent findings from the Voyager probes is the unexpected increase in cosmic rays found in interstellar space. This discovery has prompted scientists to rethink their theories about the interstellar medium and the environment beyond our solar system. NASA has implemented measures to conserve the Voyager's remaining energy and prolong their missions as long as possible. The spacecraft are expected to remain operational until at least 2030, continuing to provide valuable data that will deepen our understanding of the interstellar medium and the outermost regions of the solar system. The Voyager mission's endurance and success showcase the creativity and dedication of the scientists, engineers, and technicians who designed, built, and managed these spacecraft. Despite extreme conditions and vast distances, the Voyagers continue to operate, delivering data that has revolutionized our knowledge of the solar system and beyond. These missions have also highlighted the importance of robotic exploration in advancing our understanding of the cosmos. The Voyager mission's success relied heavily on gravity-assisted techniques, which allowed the spacecraft to reach distant destinations and gather invaluable data. These techniques, which involve using the gravitational pull of large planets to propel the spacecraft forward, enabled the Voyagers to undertake their legendary interstellar journeys. In our solar system, spacecraft can propel themselves forward using gravitational slingshots rather than relying solely on their engines. By using this clever maneuver, they save valuable fuel and increase their speed, allowing them to reach more stops on their grand tour. A gravitational slingshot or gravity assist transfers a portion of a planet's orbital momentum to the spacecraft, boosting its velocity and enabling it to travel further into space. When a spacecraft passes by a planet, it can transfer some of the planet's velocity to itself, a technique known as gravity assist. Imagine Voyager 1 traveling toward Jupiter, a massive gas giant with a powerful gravitational pull. As Voyager 1 swung by Jupiter, it did so at the precise angle and speed thanks to the meticulous calculations by NASA's brilliant minds at the Jet Propulsion Laboratory. This maneuver allowed Jupiter's gravity to accelerate Voyager 1, giving it the necessary boost to continue its journey. However, executing a gravity assist is a delicate art. Had Voyager 1 approached Jupiter at an incorrect angle or speed, it could have experienced a catastrophic failure. The level of precision required is extraordinary. Yet the engineers and scientists responsible for those cosmic maneuvers made the right decisions time and again. These gravity assists enabled both Voyager 1 and 2 to embark on an incredible journey through the solar system and beyond. For instance, Voyager 2 relied on gravity assists from Jupiter and Saturn to reach Uranus and Neptune. These gravitational dances were crucial to the success of the Grand Tour, a mission that might not have been possible without these slingshots. Thanks to the accuracy of these gravity assists, Voyager 1 and 2 eventually reached interstellar space. Although gravity assists are based on a simple concept, their implementation is incredibly complex. The grand tour of Voyager 2 demanded extreme precision. A failure to execute any of the gravity assists could have resulted in mission failure. However, the mission team's relentless pursuit of knowledge ensured success. The Deep Space Network, or DSN, also played a vital role in the extraordinary success of the Voyager missions. This network, which supports interplanetary spacecraft missions, consists of large antennas and communication facilities spread across the globe. The DSN's primary job during the Voyager missions was to maintain communication with the spacecraft, allowing scientists to exchange data and send commands from billions of miles away. As Voyager 1 and 2 ventured further from Earth, their communication and tracking systems became increasingly important. The 3 DSN locations, Australia, California, and Spain, ensured a constant connection, enabling the transmission of crucial scientific data back to Earth. The Voyager spacecraft themselves were engineering marvels. Their sturdy platforms were designed to minimize visual blur while capturing photographs and data as they sped through space. As discussed previously, the spacecraft rotated very slowly, allowing the Voyagers to make significant discoveries about the outer planets and their moons. Comparable to the interstellar phone line that connected us to the intrepid Voyager probes as they journeyed into the unknown, Deep Space Network was essential. Although the DSN might lack outward appeal, its significance is equal to that of the spacecraft it supports. Massive radio antennas strategically positioned around the world, especially in California, Spain, and Australia, make up the DSN. With diameters ranging from 26 meters to an incredible 70 meters, these colossal dishes act as cosmic megaphones, allowing us to communicate with spacecraft far beyond our planet. The DSN was indispensable to the Voyager mission's success. The Voyager probes, with their cameras, sensors, and other instruments, served as our eyes and ears in the vastness of space, returning invaluable data. A reliable communication system was essential to decipher the data they transmitted and to send new instructions. The DSN played a crucial role in this regard. Picture Voyager 1 exploring the farthest reaches of the solar system, sending messages back to Earth. These messages, carried by a faint signal moving at the speed of light, traverse the immense void of space, gradually weakening over time. Yet, thanks to the DSN, we continue to receive and decode these signals, unlocking the secrets of the cosmos. As Voyager 1 and 2 journey into the far reaches of space, their signals become more than whispers by the time they reach Earth. But these faint signals don't just vanish. Thanks to the DSN, these whispers get picked up and amplified. The DSN's massive antennas, finely tuned for the job, ensure that even the most distant spacecraft can communicate with us and get the instructions they need. The DSN doesn't just catch these faint signals, it also sends commands to the spacecraft. Scientists and engineers regularly update plans, reroute spacecraft, or tweak sensors on the fly. This constant adjustment is crucial for keeping the missions on track. Without this two-way communication, we wouldn't be able to make the necessary tweaks to ensure mission success. What makes the DSN so impressive is its ability to stay in touch with spacecraft no matter where they are. Its global network of antennas lets us communicate in real time with spacecraft, even if they're billions of miles away. The antennas are so sensitive that they can detect the faintest signals traveling through space, a must for deep space missions where every bit of data counts. The DSN operates through 3 major complexes: Goldstone in California, Madrid in Spain, and Canberra in Australia. These complexes house some of the largest and most powerful antennas, including massive 70-meter dishes. They're strategically positioned about 120 degrees apart around the globe. This setup ensures that as Earth rotates, at least one of these stations is always in contact with any given spacecraft, providing continuous tracking and communication. Timing is everything in deep space missions. Every tiny error can lead to big data discrepancies. To avoid this, the DSN uses super-precise atomic clocks to track the spacecraft and interpret data accurately. The DSN also helps guide spacecraft by monitoring the Doppler shift and the timing of received signals, allowing us to pinpoint their position and speed with great accuracy. One of the DSN's standout features is its ability to operate around the clock, always on the lookout for faint signals from deep space. This relentless monitoring ensures that we stay connected with our spacecraft no matter how far they travel. If a spacecraft goes billions of kilometers from Earth, the DSN is still there, collecting valuable data. The DSN's extensive network provides crucial redundancy for deep space missions. Even a brief loss of communication could mean missing out on important information or failing to send necessary instructions. Thanks to the DSN, the Voyager missions were able to continue their incredible journey, uncovering astonishing discoveries like Io's active volcanoes and Europa's icy shell. And the DSN doesn't stop with Voyager. It supports a wide range of missions, including those exploring Mars and even reaching beyond our solar system. Its ability to handle vast distances and maintain strong connections is a testament to human creativity and our unquenchable thirst for exploration. As technology evolves, the DSN continues to improve, handling more data and keeping us connected with our far-flung spacecraft. Think of the DSN as our lifeline to space, not just a collection of antennas. It guarantees that the stories of the Voyager missions continue to unfold, even as these spacecraft venture far from Earth and into the uncharted realms of interstellar space. The DSN creates a bridge between our world and the vast unknown, making it possible for us to reach further into the universe. One major milestone in the Voyager probe's interstellar mission was crossing the heliopause, the boundary marking where interstellar space begins and the sun's influence fades. For a long time, scientists didn't know the exact location of the heliopause. Early estimates suggested it was close to Jupiter, but further calculations refined this understanding. In 1993, astronomer Bill Gurney estimated the heliopause to be around 116 and 177 astronomical units, or AU, from the Sun. An AU is roughly 93 million miles, the distance from Earth to the Sun. When Voyager 1 reached the heliopause around 20 years later, it observed an expected increase in plasma density, validating Gurney's calculations. However, this encounter raised intriguing questions. The direction of the ambient magnetic field didn't change much, yet the plasma density increased. This was surprising, as scientists had anticipated a noticeable shift when transitioning from an area influenced by the Sun's magnetic field to one affected by other stars. Voyager 2, which also reached the heliopause at about 120 AU from Earth, found no changes in the magnetic field either. These findings challenged existing models predicting the heliosphere's nature and its interaction with the interstellar medium. The data contradicted the theory that the heliosphere would change with the Sun's 11-year cycle, especially since Voyager 2 arrived when the solar wind was at its strongest. This should have placed the heliopause further than 120 AU, yet the data showed otherwise. Despite these challenges, the Voyager findings have provided invaluable insights that have refined theoretical models. Scientists now believe our Sun has shifted from a hot ionized zone to a partially ionized region of our galaxy, likely influenced by nearby supernovae. These supernovae heated the surrounding area and stripped electrons from neighboring atoms, creating a border that resembles a seashore with choppy waves and inconsistent magnetic fields. While the Voyager spacecraft leave behind the planets and moons they once explored, they continue their solitary journeys through interstellar space. What lies ahead for these unstoppable travelers is a cosmic guessing game. Voyagers 1 and 2 are heading towards separate constellations. It's likely that these spacecraft will endure for millions of years, outlasting our species. Even if they lose power and cease operations by 2030, they might still encounter other star systems in the distant future. Imagine an extraterrestrial civilization discovering the Golden Record, a time capsule of human history. Each Voyager spacecraft carries this record, filled with sounds and images chosen to showcase the richness of life and culture on Earth. It includes greetings in 55 languages, music spanning different eras, and much more. The Golden Record aboard the Voyager spacecraft includes a fascinating collection of sounds from diverse cultures, natural world noises, and images showing humanity's achievements and way of life. This record could spark the curiosity and wonder of any extraterrestrial beings who might stumble upon it, offering them a glimpse into our reality. Meanwhile, the Voyager probes keep sending valuable data from interstellar space, deepening our understanding of the universe. Despite their dwindling power, they continue to encounter cosmic rays, magnetic fields, and plasma densities, providing insights into the composition of interstellar space and the forces shaping our galaxy. Reflecting on the remarkable journey of the Voyagers highlights the relentless curiosity and determination driving scientific exploration. The heliopause, once a distant and mysterious boundary, has been crossed, presenting new questions and challenges for future scientists and explorers. The data collected by the Voyagers will inspire and inform generations to come, ensuring the quest to understand our universe continues. Voyager 1 and 2 stand as enduring symbols of human achievement in the vastness of space, carrying with them the dreams of humanity and the legacy of their creators as they venture further into the unknown.